Alrighty, next up we have planet scale metrics ingestion, with Andre and Sam. Please come to the stage.
Hi, guys. So I'm Andre Branchizio. I'm staff engineer in the observability metrics team.
And I'm Sam Dufel, also on the metrics team. Our team. Yeah, that's us in the boat there, building Observe together.
The AI prompt for this is epic.
Yeah, we can share it later. Rested.
Yeah, so the metric system of Observe is a beast.
Hang on, back up higher.
The metric system for Observe is a beast and fairly complicated, and we're going to focus in on just one section of that, and it's how we collect all of the metrics and get it out into our long-term metric system. And more specifically, we're going to kind of tell you a story of how we shrank the cost of the metrics ingestion by 2/3, as well as increasing reliability. So most of you, this is going to be not new information, but we'll do a really quick background of metrics collection using Prometheus. There are two methods for getting metrics out of applications, services, and it's push versus pull. It's outside of the scope to go like what the pros and cons of each one are. In our system, we actually have a hybrid of both of these different methods, but all in all, it kind of all ends up being pull in the end. So this is a rudimentary description of what push versus pull is. As you can see, the push, we have a monitoring system that is getting pushed to from the applications that have metrics. And on the right here, we have pull, where the monitoring system is actually reaching out, discovering the applications that have metrics and pulling the metrics into them. It is that simple, though, in terms of describing the different things. But we're going to actually zoom in on the right side of this and talk mostly about pull-based system using Prometheus. So if we go back here, every single one of these app bubbles, in the Prometheus world, we can kind of just talk about them as targets. They could be an app, it could be a node, it could be anything that has a hosted endpoint that exposes Prometheus native metrics. And this is what that endpoint could look like. So if you're running an application on your local host port 9090 and it's producing this histogram, Prometheus is going to go out and hit this endpoint and get this metric, pull it in, and that's what we mean by scraping a target. At Shopify, we have hundreds of thousands of targets, up to millions at peak. And so this provides, if you're, like Aaron was talking about before, if you're a small company, small startup, you have hundreds of targets, a simple metrics collection system is going to get you by pretty well, but we run into a lot of scaling issues at our scale. So this is a basic metric collection in the context of within a Kubernetes cluster. At Shopify, we have hundreds of Kubernetes clusters, and they get bigger and smaller quite rapidly. And not just that, it gets even more interesting because clusters come in and out of existence. But here is a basic diagram of what it might look like using Prometheus. You have nodes, pods, maybe some other external scrape targets. All of these have, many targets within them that can be scraped by Prometheus. Prometheus needs to discover all of these targets that exist within the cluster, then reach out to them, have a background process that's running for each target every 30 seconds, go out and scrape them, get the metrics. And what's not shown within this diagram is externally, you might have a regional cluster that you're pushing these metrics to for long-term storage. But Prometheus talks with the Kubernetes API to discover all of the services that exist within the cluster, keeps track of those, and then goes and monitors them, like scraping every 30 seconds. Okay, so backing up to a couple years ago, we had just wrapped up a metrics migration to Observe from our previous vendor. There was a lot of POC work that made it into production because, and this is a good representation of what we all looked like on the metrics team during that time. There was a significant amount of on-call toil. We were paged multiple times a day for clusters that just scaled up too fast. Prometheus would be crash looping. You'd have very manual configuration-based work for each cluster. Oh, this cluster is this big on average. I'll put a minimum HPA of this, and so on. And because it was all POC work, there was also a lot of work to control costs. Like we hadn't gotten to the point of even reducing costs. It was just survive the migration.
Yeah, so we built a workable solution, but it wasn't great. It got us to prove that we could do it, but we needed to start improving to make our lives easier, reduce costs, etc. So in our case, we expanded on some open source solutions. Instead of running one pod, we would run a set of them. We can't actually fit the entire set of metrics from a cluster on one Prometheus pod. It's too expensive to kind of keep track of all these different targets in a single pod's context. This pod's going to be talking to the API and listening for any changes to the cluster. When you're talking about tens of thousands of targets to look at, it is far too much to keep track of the memory. And like Andre was saying, these clusters are scaling up and down dramatically. There's different size clusters. Some have, say, 10 targets, some have 10,000. And the manual configuration is just not something you can do with a reasonable amount of time. So this is a look at our initial setup here. It's very similar to what you might use the open source Prometheus operator for. We would essentially set up a replica set of Prometheus pods. Each one has a percentage of targets to look at. So we hash the IP address of the targets. Each pod talks to the Kubernetes API, filters down the target list, and then is in charge of scraping metrics from its particular targets. We built some sidecars to essentially make each pod aware of the size of the replica set. So we can then say we've got 3 agents, take 1/3 of the targets and scrape those. And then we put a horizontal pod autoscaler at top of those so we could somewhat scale to accommodate the volume. But as you can imagine, these are semi-stateful systems, and scaling those quickly does not work super well. If you have a ton of extra targets coming in, we might have memory issues on one pod, it starts crashing, and then you can no longer scale. You have to go in manually and fix it.
Yeah, so Sam and I set out to improve this. We had some ideas for how we could improve it. We noticed some of the issues were because of how we were sharding and how the HPA would scale up the Prometheus agents. There would be moments where targets would move from one agent to the other. During those moments when they're moving from one to the other, you have disruption in the metrics collection, so you'd get dips when you're querying the metrics. Randomly assigning the targets, as Sam was just speaking about, it doesn't balance well because you could have one target that has thousands of metrics and then another target that has 4. So you can't, we just never had a good balance across these agents. You'd have one that was heavily underused and one that is overused, so that needed to be looked at. And then also we profiled the Prometheus. Prometheus, I should back up for a second and say that Prometheus has two modes. One is to run Prometheus as its own, like kind of all-encompassing, I can query you. You collect metrics, you're going to do long-term storage and everything. And then there's also an agent mode, which is what we use in cluster, where agent mode, it makes it so Prometheus can't be queried. It's just more of a buffer, a temporary buffer for collecting the metrics and then sending those out to some long-term storage system. So we profiled the Prometheus agent, and we saw that, surprisingly, just discovering the services within the cluster on some of these really large clusters took 50% of the memory, or 50% of the resources, both CPU and memory in some cases. So, and this is redundant work because you have multiple Prometheus agents, and each one of them is discovering all targets that exist in the entire cluster. So they're all doing the same work, and then taking only their slice of the pie of those targets. So yes, fetching the state from the K8s API is expensive and redundant. So these were what we set out to improve with what we call Shopify Prometheus Operator. So this was our first version set up to kind of handle some of these problems and make things better. So we started by thinking about how we could remove service discovery out of the Prometheus agents so that Prometheus agents could just do what we want them to do, which is scrape targets, and service discovery could handle discovering the targets. So we literally took the code, the service discovery code, out of Prometheus agent, put it in its own service, and we ran that separate here as service discovery pods. We still had many of them because this is what we wanted to also, we had kind of, it sounded crazy at the time, but we wanted to solve the problem of sharding based on IP addresses that didn't balance well a different way. So our idea was, what if we pre-scrape the targets and we weight them? So we scrape them as if Prometheus would scrape them, and we see how many series they have, how many labels those series had, and do some rough calculation to see this is about how big you are. And it's just some relative number. It doesn't really matter too much what the exact math is, but as long as it's, you know, relatively correct, two targets being bigger or smaller than each other. So we separated the service discovery code out of Prometheus agents, and we had service discovery be its own thing with a second job of actually, you know, not only discover these targets, but go and scrape them at some interval, like 2 minutes, and weight them and constantly weight them, and to give that back to the operator.
Yeah, so the operator is pretty straightforward. It gets a set of targets from the service discovery pods. It is configured to know roughly how much each agent can handle, and then it just distributes these targets to each agent. It'll kind of fill up a bin of maximum capacity for each agent, and it'll control scaling too. So if it sees, hey, I've got a new target coming in, it's too large to fit in any of my existing agents, it'll scale up to an extra one and assign it there. It's semi-stateful, so it will keep the target assignments consistent until it restarts. And let's see. It's
Bin packing.
Yeah, bin packing essentially. Yeah, it works reasonably well. We had to fiddle with the configuration a bit to pick out roughly how much we can fit on an agent. But once it was configured, it was reasonably static. Yeah, so once we launched this first version of the operator, we had pretty good results. We dropped our total CPU usage across the entire monitoring namespace by about a third. This was largely due to the fact that we didn't have to manually configure how large of a deployment we needed anymore. So the operator was smart enough to configure the approximate right size for the agents on its own. And we had, that's pretty good results.
Yeah, just a measly 10,000 CPU. And yeah, like Sam's saying, most of this is due to just the more efficient bin packing here. We haven't even handled the redundancy of the service discovery. So in our first initial version of this, we still have multiple service discovery pods, and each one of them is still doing the discovery of the entire cluster, which we knew was redundant, and we could fix that. So we went out and did a version 2 of the Shopify Prometheus operator. And in this version, we took it a step further, and we split service discovery into an additional component that we call the SD workers. So in this version, service discovery is run as a singleton, just a single pod that discovers all of the targets. And as it discovers these targets, it puts it in a queue, in a work queue, that is basically saying this needs to be scraped, this needs to be scraped, this needs to be scraped. And this is a way for the service discovery workers to pull from that queue and scrape and weight the targets and give that back to service discovery, which gives that back to operator. So in this case, we can scale the service discovery workers and have many of them. Their job is only to monitor these targets to see how big they're getting or small they're getting. And the service discovery can do only what it needs to do, which is discover the targets.
Yeah, so while we were working on this, we made some discoveries about the cost of scraping, especially unhealthy targets. At our scale, it's very important to set some sample limits on our targets. So we don't want to allow more than, say, X metrics from a single scrape target. It's pretty easy for one team to do something a little rogue and, say, drop a few million metrics onto us. That causes issues all the way through the ingestion, query, path, alerting, everything has issues at that point. So we set pretty strict sample limits at the time of ingestion. But a lot of times when you have a very large target like that, it's also slow to scrape. So we don't want to scrape it and then pull all that data down into memory and then at that point discard it. So what we can do is in these SD workers, we can say, hey, this target is already exceeding the limits. Let's just drop it right now. It saves the agents from having to deal with that load, and it makes everything run a lot smoother. Similarly, we have issues where some targets just don't exist. Someone configures a port which is not listening properly. You might get a connection to it, but it doesn't ever return any metrics. So we can filter those out there as well. Sometimes Kubernetes will leave a target in the system, but it's already gone. It's not responding anymore, and a request will just hang for 10 minutes. Go's default HTTP timeout is extremely long. So we want to filter those out as well. It's very disruptive to the agents to be trying to collect metrics from places that don't exist. So by filtering these early on, we were able to really dramatically improve CPU usage on our Prometheus agents.
Yeah, we filter them out, and we also keep track of which ones are bad. So if somebody says, hey, where's my metrics? We can say, oh, it's unhealthy for this reason. And soon we will actually alert users about that. Cool, so yeah. So surprisingly, yes, the service discovery made a pretty drastic improvement just running that once per cluster as a singleton. But a good chunk of this, I'm not exactly sure how much, but a good chunk of this is what Sam was talking about with unhealthy targets, with Prometheus just trying to scrape something that just hangs forever. So the combination of those two things led to another 5,000 CPU reduction across the fleet.
Yeah, so just to recap, from all this work, we discovered that at large scale, it sounds like a random assignment of targets will work nicely, but randomizing workloads of various sizes does not actually give you a very even distribution. We really needed to be more intelligent and do some actual bin packing calculations to decide what is going to be managed by what worker. And also, for very large Kubernetes clusters, the service discovery is quite expensive, and it does not scale well with a kind of sharded system. We had to really focus on doing that one time with a singleton to make this cost effective. And also, Prometheus does not handle unhealthy targets very well. Anything too large, too slow, will really drag down the performance of agents.
Questions?
Hey.
Have you thought about contributing some of the unhealthy targets for upstream? What's that been like?
So the question is, have we thought about contributing some of this work upstream, like the unhealthy targets? We have considered upstreaming like the whole thing. We do believe, like at our scale, the fact that this needs nearly no intervention. I mean, it's very close to no intervention, and I think we will get there over the next year or so. Makes me strongly believe it would work out of the box for pretty much everyone who has, it's lower than our scale especially. Upstreaming though, I don't know.
Yeah, it's just a matter of priorities and time. We've got lots of work to do with Observe, so if we find ourselves slow on work, we might get to it, but
Yeah, we've been talking about it for a year, so we'll see how we get.
My question about high availability. So, like, I saw you had the singleton in there. Like, what if that goes down? Also, are there like duplicate agents in case one goes down to scrape targets, or how do you handle that whole problem?
yeah, so a lot of the components they can handle downtime without too much disruption. We didn't talk too much about it, but when we're assigning targets to agents, we have a sidecar running on each agent that's going to pull data from the operator and stash it on disk. So that agent can run with the entire rest of the system gone indefinitely. It'll just keep scraping its assigned targets. So as long as nothing is scaling in or out at that exact moment, you won't even notice the difference if the operator goes away. Similarly, if the service discovery pod goes away, the operator will keep assigning the targets to its agents. There's no issue. The workers are all fungible. They just pull from a queue, and then they can be dropped if needed. They can scale in and out. It's no big deal. If we do lose the entire service discovery pod, we'll have like a brief interruption discovering new targets, but it is completely stateless. We just need a new one to come online. So unless we have like zero availability on the cluster for new pods to scale in, it's not a big deal. Most of the disruption will just be on anything new coming in will not be picked up for like another minute maybe. With Prometheus, the first scrape is usually known to be lossy anyway. You can't really rely on that initial scrape to collect every metric at the beginning, so it's kind of a known issue. Thank you.
Thank you.